Okay, so let me share my screen. Welcome to the class today. As usual, let's have a quick look at the syllabus page and then we get started on our slides. Okay, yeah, you should be able to see my screen. Okay, so this is our syllabus. So we finished week 3, week 4. Today we can do some more advanced techniques other than SVM, which we covered, which are very popular. We have random forests, we have neural networks. And then week 7 is important regardless of what technique you're using. Week 7 is about evaluating your technique. The metrics people use in evaluating a technique. What are the metrics people use to evaluate the performance of your technique? These days in some companies, there's a lot of data science focus along with other things like development and data engineering. A lot of people do understand these metrics regardless of what their understanding is of the rest of the techniques and stuff, the modeling. So especially ROC curves, these are common terms that people use in business meetings if they're using machine learning models. So this is also very important at some point. Then week 8, I've left it blank. We can bring in new and cooler areas or topics in this, or we can use it for revision or covering other things like interview preparation, etc. Or just to catch up. If you're slow somewhere, then we can catch up here, etc. Week 9 and 10 is basically, so we have 4 more weeks, about 5 more weeks. So week 9 and 10 are basic statistics concepts, because these days a little bit of statistics is also useful apart from just the cool machine learning techniques. These are concepts that a lot of people should be knowing. What is hypothesis testing, what is confidence interval, etc. Week 11 is clustering. So how do you group your data into different subsets? So there is no prediction, nothing here. You only have a set of variables. There is nothing like label or predictive response or anything. Just a bunch of variables. So it could be some variables from your SQL table, for example. How do you group them into different groups, right? So that's the clustering problem. It's also pretty useful sometimes in practical purposes in companies. So yeah, week 12 is something else. We can get to there. And then we obviously have the advanced version of the course as well, which has like deep learning and everything, time series and stuff. So we're going to do neural networks today, actually. So let's get started on that. The slides I'm using now is very popular. It's by Andrew Ng. This is actually, it was also used, it's being used in UPenn, but actually it was also used in the Coursera course to some extent by Andrew Ng, like the introduction to ML or sometimes in the deep learning courses. So this is like very common material. Just search Andrew on neural networks. You'll get this slide in some site or the other. I'm just sticking to this for now. It's more than enough for our purposes. Okay, so neural networks. First couple slides are not really technical or not very relevant, but I mean, I think they put it just to, for people who are curious about why do you call it neural network, or because neurons are this kind of the biological aspects of our brain and everything. So we wouldn't be covering really into this. I mean, this is not an MBBS course, and also this is more like this is honestly not very much really like our human brain. Our human brain is a lot more complicated than what a neural network is. This is just a model, right? So so this is very speculation. There's a lot of speculation, very speculative kind of material. So we shouldn't be covering really about this. So I'm skipping this part of it. This is all the structure of the neuron and the cell in the brain cells and stuff. So this is the part that I'm not very much a big fan of. So let's skip it. Let's go to the real part of the model, which is the point. We want to discuss the point of it. Okay, there we go. This is more relevant in terms of background or some history. Yeah, they try to mimic the brain, but this is a very a weak statement. You don't have to believe this. You can always say maybe not at all. I would still be happy. Okay, very widely used in the 80s, very true in early 90s. So initially when things like handwriting recognition and recognition of your interactive voice response when you call your credit card company or stuff like that. These things were being done by neural networks very successfully back in the day. And so those were some very initial successes of neural network, very popular. And then a lot of other techniques came up, like the support vector machines and more recently random forest and everything else. And these started performing, honestly, sometimes in some cases much better than neural networks, standard neural networks, which are known as feed-forward neural network. And then more recently, in the 2000s, with the resurgence of deep learning, which is basically some modification of the architecture of neural network techniques in general, they started performing much, much better, especially on vision data sets or vision problems where you're doing image recognition or human activity recognition, these kind of applications. It started really performing very well on all the benchmark data sets, and it was giving state-of-the-art results. So that's the whole recent resurgence about neural networks via deep learning. And yeah, this is a good statement. And yeah, with respect to all the brain stuff he was talking about before. So neural networks are not nearly as complex or as intricate as the actual brain structure. So it's kind of just a fancy name. You could have called it something else. It's perfectly be fine, as long as, even if it's nothing to do with the brain. Okay, this is the model. So this is the keep it simple kind of the look at the neural network model. This is the overall idea. As we keep going down, you will get more intricacies and more clarity about it. But basically, you have what is known as input units, hidden units, and output units. What are these? So basically, your data set gets fed into what is known as the input units. I will open this up more in the coming up slides, but this is the overall idea. And then, if you see the arrows, what that is saying is there is some weight associated on each arrow. So basically, you're weighting say you feed your first variable here, second variable, third variable, fourth variable. So you have 4 variables, for example. You weight your first variable according to whatever weight is there on this arrow, and then you send it here. Here you weight it separately. So everything gets weighted everywhere. So this is known as a feed-forward neural network, because if you see, all the arrows are going just front. There's no feedback or anything coming back. And then also, this is also a fully connected neural network, because if you see every neuron, these units are also known as neurons. Every neuron is connected to every other neuron. I mean, in the next layer. Obviously, as you see, there is no direct arrow from here to here, but you can go there or anywhere in this layer via this layer. And to keep it even more clearer, I think I should move to the next slide. There is some more information regarding the definition of the model that is involved here. So let's go there actually. But I think this slide is good to get used to the terminology. So the nodes or units or neurons are these circles. The weights are the links. So the links are the edges. I was using arrows, right? Those are the links. As you see, each link has a weight associated with it. That's what it's saying. And an activation level. We'll talk about activation function when we come to the next slide. Each node has an input function, typically summary. Yeah, this is better mentioned here. It's more clear here. Neuron model. This is as simple as you can get. Say you had nothing. You only had one layer, and then you have the output. Just to simplify, it is not how simple we use a neural network in current practice, but it's good to understand what is going on in a zoomed up level. So these are your X's are your input values, your input feature variables, 4 variable data. So these are the edges, right? The links. And they have weights. Here they are denoted by thetas, theta naught, theta 1, theta 2, theta 3. So what is happening once you take all these from one layer to the next layer, or from the output layer to the final, giving out the output from the computer on what your classification or regression is? All that is happening is basically a sum of products operation. What does that mean? And then what is known as an activation function. So here the sigma is denoting the sum. This is denoting the activation function. That's what he wants to show it is happening in here. But what does that mean? All you're doing is sum of products, which means theta naught times x naught. It's a product. theta 1 times x1, theta 2 multiplied by x2, theta 3 multiplied by x3. You sum all those four products. So it is theta naught x1 x naught plus theta 1 x1 plus theta 2 x2 plus theta 3 x3. That is the operation happening here in terms of the sigma, which is what can be written in matrix multiplication form. This is a row vector theta times x. So you know how a matrix multiplication happens, which is the same as this thing, sum of products. So it is written more succinctly like this. And G is the activation function, which is this operation that it is denoting, this graphic in here, which is you do the sum of products. So you do theta naught x naught plus theta 1 x1 plus theta 2 x2 plus theta 3 x3. You get some number. That number, you pass it through a more complicated function. Here, the function you're passing it through is the G, which is defined as the sigmoid function. Here he wrote it. Sigmoid, also known as the logistic, more popularly known as the sigmoid activation function. This is another part of the neural network, the activation function, which is defined as this. So you do the sum of products, and then you do 1 by 1 plus e power minus that value you get with the sum of products. The theta transpose x is the sum of products. So G of theta transpose x. So 1 by 1 plus e power minus z. In Z, you put in theta transpose x. That's how the activation function is defined. So what are we doing here? We're just defining different aspects and terminologies and different operations involved in a neural network at every layer, right? Any questions? Feel free to interrupt. So now we are again coming back. We just zoomed up at this level, right, or this level, and saw what happens from one layer to this layer when you go here and you apply the activation function. We saw that in the previous slide here. That's what we saw. Now we are looking again back to the original where we started. We said there are layers. The first is the input layer, which is basically your data. That is where you feed your data, your access. Then there is hidden layer. Now, to be even very specific, you don't need to have only one hidden layer. It's not necessary that it's always one. You can have as many hidden layers as you want, as is required by the problem. So you can have 10 hidden layers, 100 hidden layers, depending on how complex the problem is. And then you have the output layer, which is what it's going to happen in the output layer. So this is a even more accurate representation than what you saw here. Here is not like I just put in like 3 bunches of layers and I've not really shown what is happening. But here it is more accurate, and this is as accurate as can get. The only difference you can have if you want to make it even more accurate is you can say, obviously you have only one input layer, you always have one output layer, but in the middle here he showed one hidden layer, but you can have as many hidden layers as you want. So this layer goes into another layer, everything gets connected just like it got connected here. You can keep going like that, and then finally you collect and aggregate your answers here with an activation function output layer. So that will be the most.
So Praneeth, here what is the difference, the dotted line versus solid line? So dotted line is nothing but there is no end to end.
No, that's a good point actually. That's a very good point. So the dotted is, so what it is saying is the x0 is not really input data. He's saying only you have 3 input data points in this example, x1, x2, x3. x0 is like an intercept or like a bias term. So say linear regression, I will show here quickly. So usually what is an intercept in general? In linear regression, we have y equal to mx plus c, or y equal to x beta plus c, which is this is the equation of a line or a plane, straight line, right? The thing is, x is your input data, so this term is dependent on your data term. This is obviously what you're trying to predict here, right? But there is a term c, this is the intercept. This is a term that has nothing to do with your data. So what this is doing is, if I'm drawing a straight line, I mean, this is a cartoon, this is supposed to be a straight line. These are different kinds of straight lines. Every straight line meets the y-axis at some point, right? So that is known as the intercept. This length is known as the intercept. So that is the c. But this is the line. This is basically just deciding like this. The shape of your line is the same, but it's just deciding where it intersects the y-axis. So there's a bigger overall point here. There is always going to be some amount of terms that you can explain with respect to your output using your input data. There will be some function of your input data. But there will always be some additional term you can just add to it, which is not dependent on input data. It is just, you fit your function, you're just making sure you're placing your function at the right place. So you can see is just moving it so that it is going to pass your data even better. So this is a non-data dependent term. So similarly, your f of x, since we are not doing linear regression, since we are doing neural network, your f of x is basically the part of the neural network that gets affected by the x values. So these are all affected by x values, your input data. There is some parts of the neural network which is not affected by x at all. X0 is not a data point, it's just an intercept. So this is the weight corresponding to that layer. That's why he put it in dotted. And he mentioned that clearly in this previous slide, right? He's calling it bias instead of intercept. So this is the bias unit x0. So say, for example, x0, you can fix it beforehand to be 1, for example, or it will be decided by the model when you fit it, what number it should be. But it is not dependent on data. So x0 doesn't come from data. That's what it is. So this is the overall architecture. Another term is architecture of neural network, because this is feed forward. We saw there is no loops, nothing coming back. So this is known as a feed forward neural network. There are different kinds of architectures, and the architecture is what makes deep learning techniques different, right? So there are different architectures of neural networks. Some are deep learning architectures, basically. To be even clear, there is a feed forward version of deep neural network, which is you have the exact same thing, but you have many hidden layers. So usually, typically, people use 1 or 2 for many problems, hidden layers, and it does more than enough performance. But sometimes problems are very hard, and then people might use 100 layers. That's why they call it deep neural networks. So that is the most simplest deep learning technique. And deep learning, obviously, you know how popular it is. Like everyone is sharing everything, regardless whether they know anything about it or not. But deep learning, everyone talks about it. So if you have many layers, it's deep neural network. But that is not the only deep learning technique. Deep learning is like a paradigm. There are many other architectures as well, which could be deep neural networks. The feed forward, this is the terminology we used already. What is the purpose of the activation function is an important thing. And what is the purpose of the input function, or what are your links doing? We've discussed this, but he has written it in English here. So the input function, right? Usually this is just the weighted sum of the activation of the links feeding into this node, which is what it's been clearly mentioned here. It's more explicit than English here. You're doing the theta transpose x. The weighted sum is what it is at every link. Activation function. Why are we using activation function? That's a good point. We've not really discussed it. He's mentioned it here because what the activation function is, you know, it is transforming your input and all the processing you're doing into a final value. Because, you know, say I want to predict whether email is spam or not spam. I want to take input variables as emails and all variables derived from emails. But my output should be, say, 0 if not spam, and it should be a number 1 if it is spam. So if I do theta transpose x, and if I apply this function, activation function, if I don't apply activation function, if I do this operation, theta transpose x every layer and keep going, but if I do not apply the g, what will happen is theta transpose x will not be either 0 or 1. It could be any number. So it is, then you won't know. If I give a number, say 5 or 500, then you will ask me, hey, neural network is saying answer is 500 for this email. Does 500 mean spam or no spam? We don't know. We wanted 0 or 1 so that it is clear for us, right? And sometimes it might return some other number. It might return as many numbers as possible, because theta transpose x is not restricting that you will only get 0 or 1, right? If you multiply 2 numbers and add them up, if you keep adding up, it will not be 0 or 1 most of the times. So G is making sure that everything processing gets done. Finally, when you apply G, the activation function, you will literally get some number very close to 0 or 1. That is what this function is doing. And let me show you the shape of sigmoid function. You will see why it will only return something close to 0 or 1 most of the time. This is going to Google Images. See, if you see this, this is say a sigmoid function. So your x could have been the sum of products itself, the x-axis. The y-axis is what it is returning. Most of the number, for most of the part of your input, it is returning 1 in here. Most of the part of your input returning 0 here. This is the part where you have little uncertainty, whether it is closer to 0 or closer to 1. Like this could be 0.1, 0.2, but it's still closer to 0. If it is here, then you're really uncertain. If it returns 0.5, then you don't know. It is right in the middle. It also doesn't know whether it is spam or no spam. But that does happen only very one point. But for most points, it turns something close to 0, something close to 1. So you know with what likelihood it is saying it is spam or no spam. So that is so it's a very specific activity. It's got a beautiful shape and some purpose to it. It's not any function. So, and its only aim is to transform it into a form that is useful for you to take your decision making in your company or in your academia, whatever your research. So that is the purpose of the activation function. Let's keep going. Again, this is a nice slide. It's very specific, right? It's not like in English, it's showing clearly what is going on. So say you're looking at a same neural network we saw previous slide, a one hidden layer feed-forward neural network. He's again opening up some more aspects of the processing, right? Because we only zoomed up at one neuron and saw what is happening, but here he's showing everything written down. So again, little terminology. X's are the inputs, A's are the units in your in your hidden layer. This is your output layer. H is basically whatever you get at the output layer. You're basically applying the activation function. So as we talked that at any point, to get any value here in any node, all we have to do is from previous layer, we have to do sum of products. So this is a sum of products, as you see, theta naught x naught, which means say this one plus theta 1 x1 plus theta x1. So you're doing that. Then you're applying activation function at every layer. You get some number at every layer. Again, these numbers get fed into the next layer. So here there's an equation for A1. You do theta naught x naught plus theta 1 x1 plus theta x2, but the theta are coming from these arrows. So let me be specific. This is a small figure. Let's do one neuron, for example. Then you will know everything else is the same thing. If you look at, you want to figure out what A1 number should be. You know what your input is anyway. This is your data points, your values you have. So you say what you do is, here he didn't put a bias term. There is supposed to be a bias term as well. So theta naught x naught is a bias term. Then these are the terms influenced by the data. So now this arrow, theta 1 x1 will be this arrow, the weight on this arrow. Then theta 2 1 to x2 will be the weight on this arrow, that is this theta 1 2. Okay, times whatever number you have in x2. Then again this arrow, because this is the arrow that influences A1. So these are the only arrows that influence A1, right? The ones going into A1. That is what only those weights are these weights are the arrows, the weights on those arrows. This is the bias term. Okay. Same thing. Now you know what you can do for A2. What are the arrows going into A2? What are the weights on those arrows you're supposed to have? You do sum of products. For A3, same thing. Sum of products. And after sum of products, you apply activation function every time. All that is done. Then you have values. You can populate these values here. So A1 will have some number, some real number, some number, some number, after all this processing has been done. So the number will be either close to 0 or close to 1 because you are applying sigmoid activation function. Now again, same thing happens here. Here there is only, everything gets collected here. So you are doing the weight on this arrow times A1, the weight on this arrow times A2, the weight on this arrow times A3. You're summing up all those three. So you do that. Again, you apply activation function, which is what is shown here. See, if you see, here all dependent on x naughts, but since you came to this layer, it is always dependent on the previous layer. Here you're multiplying with A naughts, A1, A2, A3. So this arrow is what he's showing. So the same thing I showed up in the second slide is being zoomed up again and again at every unit, at every entry. The concepts are same. There is no new thing involved here. We defined all the functions and units, nodes, edges, everything. Okay, we'll do that, and that is the process that is happening. Now, what is the unknowns that you're learning here? The unknowns are the weights. If you know what correct weight number you should have on each node, so that your performance is better, then you have a good neural network. If you put whatever weights you want manually or without any reason to it, then your predictions may be very bad. It may be saying all spam emails are no spam, or it may be always be saying whatever you give, it will say it is spam. Your performance is not good. But if you're doing very well, then it is classifying spam and no spam correctly. So it's all dependent. What you're learning is a few things. What these weights are supposed to be, what number you should really have in these weights, which are the thetas. Another thing you want to learn is how many layers to use. Is one layer good enough, or do I need 100 layer, 2 layer, whatever? Hidden layers to use. The third thing you're learning is how many neurons you have in each layer. You're not required to always have only 3 neurons in each layer. You can have 100 neurons in layer, 20 neurons, it's up to you. But again, you can have 2 layers where one layer has 3 neurons, one layer has 20 neurons, or maybe first layer has 30 neurons, second layer has 5 neurons. And you can have as many layers. So what are we learning? Number of layers, number of neurons, what are the weights. These are the three things you need to know to fully specify your neural network to do the computation and get your output. But these need to be selected properly so that your classification performance is good. Okay, this is a vectorization step. This is from a coding perspective, right? How do you write these in a matrix form? So what we did here, all this equation, this is the same thing we discussed in previous slide, can be written in a nice, better way in this form, basically. So basically, you take the first input, you compute the theta x terms for everything, and which is this part. So that is, then that goes through the activation function. So you call this C2, it goes to G of Z2, you get the A2 value. Then you get Z3 value by using A2 value. So it's like a recursive thing if you see. First layer feeds second layer output values, and second layer feed the third layer, or finally you feed the output layer. That's what it's showing. So apparently when you code it inside, when you're doing like GPU based neural networks and all these things, more complicated implementations which you use directly from packages, they use what is known as vectorized computations and everything. So this is more computational efficiency standpoint. He's saying there's a lot could be done internally, but he's not mentioned about it in these slides, nor am I trained to talk about that. I'm more of a modeling guy, so we are sticking to what the model is. It's what matters in our slide now. And he's not given information of, what is the best industrial implementation of internal implementation so that neural network runs in like within a second or something. That's the point he wants to mention. He says vectorization, but he doesn't mention how it is done internally. So let's forget about it. Okay, other network architecture. This is a good point. So what we saw is one architecture, which is this one, feed forward neural network. Here he's showing 2 layers, for example. So this here is again 2-layer neural network fully connected. Sometimes you don't have to have fully connected. Maybe sometimes you won't have arrows existing at some places, right? And so on and so forth. You can also have multi-output units, which means in the end your output will be not just spam or no spam. You can choose between more than 2 categories. So is it a pedestrian, is it a car, is it motorcycle, is it truck, for example, or more than that. So your output will return like this. If it is pedestrian, other values will be 0, one value will be 1. Then the values for car like this, for motorcycle say like this, for truck like this. So then it won't exactly be 0 most times. You might have like 0.87 or 0.93 in here, and these values are closer to 0. Then it is saying with more likelihood it would be whatever this label indicates when this is 1. It could have been pedestrian. That kind of thing. So that is another modification. When you have more than spam or no spam. If you're only having 2 categories, then any number between close to 0 or 1 is enough. But if you have 4 categories, you have 4 values, right? Which value is more confident? That value will be more closer to 1. Rest will be close to 0. This is the multi-output thing. So yeah, binary classification 0 or 1. Multi-class classification for neural networks. Same thing he's showing. Okay, so this is the sigmoid function. I showed you in Google Images. Good, he showed here as well. There are different versions of sigmoid, but this is one version of sigmoid function. And also the computations internally, we have the Boolean and, not, or operations. We have it in all languages, like in C, C++, Java, Python, whatever. So you can also use these operations apparently to do the sum of products operations and stuff. He's not mentioned it very clearly, but those could also be used to do your implementations. Okay, so yeah, I want to put things that are relevant here. So yeah, this is again relevant, for example, but we are not doing image processing. What he's saying is your image is like this, right? Some number of pixels, so maybe 256 by 256 or 20 by 20. Each image, right? So what you can do is each image you can vectorize it. What does that mean? Unrolled, which means, say, this thing I have to draw to keep it clear. So what is image represented internally? It's basically a matrix of numbers, right? What is the intensity of at each number, at each pixel? So in each image you have some numbers at each pixel, right? continuous. Every number is a pixel, some value you'll be having. Now, so this is just like a matrix, right? You have rows of numbers. There are columns as well, right? What you can do is you can take each row, you put it those numbers like this, then second row you add from here, third row from here, which means I'm making a matrix into one single array. So like a 2D array into a single 1D array, right? So if this is a 20 by 20 matrix, your image, then here it will be 20 times 20, right? 400 rows, but just one column, 400 by 1. Or you can write it as one row, 1 by 400, if you transpose it. So you do that, that will be your feature vector for each image. So here, say this is a problem of, so someone wrote digits with handwriting, so human written digits, handwriting recognition. Right? It is digit recognition problem. Classification, you want to classify which digit it is just by looking at the image. So what you do is, you say this is, we can see human eye, it looks like 7. So you take this image, you convert it into, you unroll it into this form, it becomes a big vector, big array. Same thing, you do that for each image. Then you pass in, those will be your samples. So then you can pass in those as access, right? So you pass that as your input. Then for each input, it will, the neural network, if you fit it correctly, if you use right neurons, layers, everything, learn the correct weights, then it will output something in this form. So you have 0 to 9 possible digits, so it's a total 10 possible classification. So you'll return it in this form, the multi-class form. But you'll, instead of 4, you'll have 10 here. Whenever it is digit 1, you'll have closer to 1 here, rest will be 0 when it predicts. For 2, you'll have 10 digits here, but second digit will be 1, close to 1, if it is really to predicted as so on. So in the multi-class representation, that's what's happening there. Okay, so finally you're getting output 0, 1 or 9 based on which number closer to 1. Okay, now the learning part. We defined all the terminologies and units in a neural network. What are the different concepts? Now here is, and we also defined what we need to learn, right? The number of layers, neurons, number of neurons in each layer, what are the weights for each neuron. That is the learning part. So that is this part. How do you figure out that? So perceptron learning is too old. This is back in the day, 1969. So this is not what is used today, so I'm skipping it. What we are using is, these days, is known as backpropagation. That is a technique that we use to learn all these unknown values in our neural network model. Okay, here he wrote slightly in English, but as we go down, it will become more and more clear what is happening internally in the computer. But the overall idea in the English form is the follows. You try to generate some weights, okay? So you do some, say you start with random weights, you just assign something. You iteratively improve your weights to a point where then you're classifying correctly. So then once you put whatever weights you want, since you don't have any information, you will then observe some output. The output may not be as good as you want in terms of classification performance, but regardless, it will give some output, right? It's like garbage in, garbage out. If something goes in, something has to come out in your architecture. Some numbers will come out. Now you look at the output, and of course, if the output is correct, no changes are made. It's very highly unlikely. You're such a complicated set of numbers you're choosing randomly. It's very highly unlikely that it will be correct. There will be some error, maybe a lot of error, some error, whatever. So if there's an error, all you can do is you can adjust the weights or change your architecture. So you look at your output based on some initial randomized weights. Then you see the error, and based on the error, you will adjust your weights. So that your aim is to reduce the error. That way you want to adjust your current weights. And you do that again and again and again. So it's taking feedback into account in terms of performance as a feedback, and then it's improving. So this is known as the overall guideline or the guiding force strategy of the backpropagation algorithm. So that's what he's saying again in English form. The trick is to assess the blame for the error and divide it among contributing weights. Okay, now the question is, how do you measure error? Right, and what is your objective function? So logistic regression is a separate technique, but we are dealing with neural networks, so we look at this just to stay to the point. Okay, so there are many different kinds of errors that you could use. I think you should be mentioning the entropy somewhere. Okay, anyway, okay, so why the reason you put logistic regression here is if you see this objective function looks similar to this, what is going on is the follows. There is a concept of log likelihood. We've not discussed this. It's a more mathematical concept that is used in knowing the, and training and learning the unknown values in what is known as generalized linear model in GLM. So this is the log likelihood, and this technique is called maximum likelihood estimation. Maximum likelihood estimation. This is purely statistical concept. It's a bit rigorous. The idea is follows. I mean, this has nothing to do with neural network, to be honest. This is something that is used in a lot of models. Log likelihood is like a concept in general. It's a statistical concept. So what you assume is the follows. We know what probability is. If you go back to our basics, probability density function or distribution function is a function that returns. We call it PDF. That's denoted by say f, for example. It's a function that returns a probability. So you take some number. This number can be any number. It doesn't have to be 0 or 1, any real number. It always returns some number between 0 and 1. So that is a probability function, right? Because probability is always between 0 and 1. That's a mathematical rule. Now, then there are, this function is known as the probability density function. So say for Gaussian random variable or like normal random variable, it looks the famous bell curve. The bell curve could be narrow, it could be very wide, it's up to what the variance is. But to be even clear, this function is not just a function of x, it is a function of x given a set of parameters. Say, let's call it theta. Then you get something between 0 and 1. So what is theta? Theta decides the mean and the variance, for example, of your density function. So this has less variance, the innermost. This has a little more variance. This has even more variance, right? This is the mean is somewhere here. The mean is here. For this, the mean is somewhere here, the average, right? So this is the probability density function. Now, what is likelihood is the other way around. You want to figure out what theta is more likely given your data set. So you want to know, this is the likelihood function, it's a function of theta. So now you will get the correct picture. Now I'll connect everything. So see this image I'm drawing in the bottom. Say first I say I'm modeling the distribution of heights of students in a class. So obviously very short students, you won't have many. This is just a histogram I'm drawing. This height, maybe these many students. Maybe this is the average height. You'll have a lot of students. It's just a bar graph, like a bar chart, like a histogram. And then again, these are super tall students. Obviously, like how many, say you're talking of 10th class, 10th standard. How many students are 6 feet in 10th standard? Very unlikely. So very few or closer to 6 feet. Or how many students are like less than 5 feet or less than 4 feet 5 inches? The shorter people lesser. How many students are somewhere between 5 feet and 5'7" or something? That is this part, right? So your x-axis is the height, y-axis is the probability or the count. Well, here it is the count, but you can also have the density function, right? So this is the density function I'm drawing. The bar graphs are the counts, but the density function is this thing, right? So this looks like a Gaussian random variable. Right? So it looks like on average height is somewhere here. This is maybe 5'4" or something, 5'7" or whatever it is, 5'8". This is the tail probability. Here the probability is less. Average height has the highest probability in this particular case. So super short people less probable in your class. Average height more probable. Super tall people again less probable. There will be few people obviously. These are the tail values of the probability, right? Now this is a very specific probability density function. It's not, see, there is many possibilities you can draw in terms of mean and variance, but there is one specific mean and one specific variance. So your theta is basically, it will be even specific an array of say mean and variance, mu and sigma. So this is a specific density function that is fitting your data. If your mean was equal to 5.7 height, or maybe I don't know 5.5 height, and your sigma was whatever, I don't know, maybe 2, variance is 2 or something, right? So, or maybe 1 or something, right? So 6.5 and this side 4.5. Everyone is between 4.5 and 6.5, but average is 5.5. Which is the variance is 1. So what? So initially I only gave you data of heights. Then you figured out the counts. Then you got the histogram. Till there everything I gave you from data itself. But then you want to figure out this curve, the probability curve, something that tells probability based on height. If I give you what height a student would be in 10th class, you would say is it highly probable or less probable or somewhere in the middle, what probability of observing that height will come out. But you don't know F until you know what mu and sigma to choose. Do I choose this for my height or this or this? There are many kinds of curves I can draw, right? Which curve do I use? Which means which sigma and mu do I use in terms of average and standard deviation, so that I will get the curve that will explain the probability of heights in a class 10 the best possible way. So it is an unknown, right? Theta you need to figure out. Is it how that it is 5.5 and sigma is 1 or whatever the true answer is. So to figure that out, what people do is they use the same function but write it as a function of theta and they try to maximize it. What does that writing it as a function mean? The PDF for Gaussian function is basically 1 by root 2 pi sigma e power minus x minus mu square by sigma square. That's a big formula I just said, right? But I will show it to you. If you do normal distribution, what I said will be here. This function is your probability density function, 1 by root 2 pi sigma square e power minus. What is this? Here the unknowns are sigma and mu, which is what we were talking about. So this is just, I'm expanding what the definition of f is. I said it is a function of x and theta, or x given theta. But I want to show what that definition is. So theta is basically mu and sigma, and then everything else is known. X is your data set. So it's a function of x and your theta, which is mu and sigma. This will always return something between 0 and 1. This is a Gaussian random variable. So normal distribution or a Gaussian distribution. But there are many kinds of distributions, of course, but this is just an example. Even if you do Poisson random variable, some other binomial random variable, it's still the same concept of PDF. You will have some parameters, you'll have data. Okay. So now this function can be treated in both ways. If you treat it as a function of, where is it? Here. If you treat it as a function of x given theta. So I give you some value of mu and sigma. Say I will say mu is 5.5, sigma is 1. And then I will say these are the heights of students in a class. Then for each height in each student's height, you will say how probable his height is in the class, right? By just computing this number, this function. You just calculate this, you get something out. But if I say I will treat it not as a function of x, but I want to treat it as a function of mu and sigma. Mu and sigma is unknown and x is given. Sorry, it's a function of mu and sigma given the x. So x is given. Then I will have to figure out what mu and sigma will maximize this. Then that is known as a likelihood function. So all the point I'm saying is this is probability density function. It is treated as a function of x given theta. But if you treat it as a function of theta given x, then it is known as likelihood function. Likelihood. This is the likelihood function. This is the probability density function. So what is the maximum likelihood estimation? The point we were talking about is we want to figure out what is the parameters that will explain the probabilities and of our data set the best possible. So that is defined by the likelihood function. You want to maximize, you want to this likelihood. So given the data, what curve is more likely? So here out of these 10 curves here, this particular curve is most likely in explaining this behavior of heights of students in class, right? So that's why you want to maximize the likelihood. And you want to maximize it as a function of theta. So you want to choose the right theta that maximizes this. Then you get the right function out of this whole possible choice of functions. So this is the concept of maximum likelihood estimation, MLE, or maximum likelihood estimation. This is how unknown parameters are learned in statistical models. When you go into the math part of it. So there's so many things about maximum likelihood estimation and search for it. This is the idea there. So this is basically the likelihood for your classification problem. And then thetas are your unknown weights. So that is what he's using here. He's using the likelihood function so that you want to maximize the likelihood so that you'll for the right amount of theta. So you learn the theta is a function of theta given your data set, theta given x. That's what this is, theta given x, right? theta, function of theta, but x is given to you as data already. So you want to learn what theta will maximize this likelihood. Okay. And to be able to compute the likelihood, you should know what distribution you're using. Here for classification, he's using a binomial distribution. So this is the likelihood of a binomial distribution basically. If I did likelihood of binomial distribution, just open something. I think the math is loading. Okay. Yep. If you see the likelihood function, binomial like log likelihood function, you apply the log to the likelihood, and it's called log likelihood. It's in this form, x log p plus n minus x log 1 minus p, right? That is what is going on here. X log 1 minus p. So x log p 1 minus x. So y. So it's like y log p 1 minus y log 1 minus p. Same thing. So in the drawing I did, I showed you likelihood concept by showing Gaussian random variables, the bell curves. For classification, people use binomial because Gaussian is a continuous random variable. Binomial is a discrete random variable. So if I'm saying 0 or 1, only two possible entries. I'm not saying height is 3.5, height is 3.7, height is 5 feet 6 inch. There you're taking all possible values. Then you use continuous random variable. In classification problem, you only have two possibilities, 0 or 1, or maybe 0 to 4, whatever it is. It's a discrete set. I cannot say it is email and a half. It is either spam and a half. It's either a spam or no spam. Right? So only numbers, integer possibilities, discrete possibilities. So that's why they model it not using Gaussian, using binomial random variable. So every random variable will have a probability density function. It will have a likelihood function. So same thing. In Gaussian, I showed you density function on wiki, and then I told about likelihood. Here, he's showing density for binomial, and then likelihood he showed here. So he's using that to model the classification function. But you have to figure out what function to use, what mu and sigma, what weights you should have, and everything. So that is being decided by optimizing. So you're optimizing by learning the weights. Okay, then the backpropagation part. You start with some weights, you compute everything till all the entries, then you observe the error. Error you observe is, say, he's denoting by delta, is the error at, so, and then what you do, the error is divided according to the strength of the connection between hidden node and output node. So then the blame is propagated back. This is again the overall English idea in English, right? The backpropagation idea. Oops, this is a good figure. So this, you learn everything and then look at errors at each node and then you propagate it. Whichever node is influencing the error the most, that node gets corrected the most basically. Error of node J in layer. So how do you know how much the error is being also called cost in here, how much the cost or the error is being influenced by each node? You get it, the influence you get it by doing the derivative with respect to that node, right? Because the derivative is what? Rate of change. If this node value changes a little bit, how much will the error change? So the node for which with slight change of your value, the error changes the most, which means it is most influencing the node. Now, mostly influencing the error. So if the derivative is big. So you want to improve that node the most because you want to catch the culprit, the biggest culprits that are causing the biggest error to you. So that you can figure out by looking at the derivative. That is the intuition. So based on that, you update your nodes. Okay. This is the backpropagation algorithm. So this is the overall idea. You learn, you compute you take the data X, you compute all your A's, all the nodes, then you look at the error at each node. Look at the gradient means derivative, you look at the gradients. And then what you do is a gradient descent. So you change your values in the direction where the gradient the derivative changes the most. So like that you perturb your values. That's the backpropagation algorithm. And then he's talking about implementation steps. So this is very specific to say Python or whatever. So we don't want to discuss these data types and stuff, but you can implement it anywhere. So putting it all, this is like a conclusion slide. It's just repeating whatever we are doing. Training a neural network. Pick a neural network architecture. Do you want to use this? Do you want to do these many layers? Do you want to do these many layers? Or something else, right? You want to use more complicated. So what does that mean? You have to figure out how many input units, which is the number of features that is fixed already, how many variables here, but number of output units is the number of classes that also. If you want to predict only 2, you have only 2 output units. If you want to predict 4 classes, then 4. And then reasonable default is 1 or 2 hidden layers, but obviously you can have more hidden layers. So basically, this is again the backpropagation. He's repeating the same thing. Implement backpropagation, then update things. Okay, so that is end-to-end of feed-forward neural networks. It's a very popular technique, and it is the starting point to the whole area of deep learning. It is our call. And we also reach our time. So yeah, so that's what I have here. Any questions? Or if you don't have immediately, this is a big area. We've covered in 1 hour. If you have something coming up, you can email as well. We can discuss in follow-up class. We also have one class where we left it empty in our syllabus where we can have these kind of discussions too, if you have any questions.
So is there any basic or simple projects that we can work on to start to get some knowledge about the neural network?
Yes, I will show you a good project. I just stopped sharing my screen. Do that. So very popular is the MNIST dataset, MNIST, M-N-I-S-T. It's handwritten digit database. This is MNIST, machine learning beginners. So this is the dataset in some. Jan LeCun is like a very famous professor in New York University. He has moved. He's also working in Facebook, leading deep learning in Facebook. He has pioneered a lot of deep learning stuff. But anyway, there's an MNIST database, which is a very nice popular benchmark dataset people use for a lot of neural network and deep learning. You can download that dataset. What is the dataset? It's basically your handwritten recognition. Let me show you. I have some image. It's something like this, right? But obviously a lot more numbers than this. So you have a lot of handwritten images of digits. So you want to train a neural network that will recognize by just looking at the image what it is. So if you do MNIST and then if you do neural networks, if you do classification MNIST neural networks, you can download the data set. You can also get some blogs and codes which you can find that will show you how to run neural networks in R or Python, or you can use more advanced versions in Python, like TensorFlow is a very popular package. You can use it for or Keras. Keras is simpler for NN and deep learning. TensorFlow, both are very popular. TensorFlow, little more complicated package. So they're very popular, used in all places, Google to small companies and manufacturing, all kinds of companies. Then if you want to use just your language-based package like R package or Python package, then there are other ones as well. Then you have a neural network package. You have scikit-learn in R. You want to go through some blog articles of how to do neural networks with MNIST database. Just replicate it. Once you have a code that works end-to-end, and you understand the methodology as well, you can keep improving. And also the cross-validation concept which we learned in SVM on how to tune constant gamma, same concept here is also used. You have to cross-validate. You try a different choice of parameters, whichever gives best cross-validation error that you will use. All that you will see when you work through these things. Obviously, I showed you the theory part and everything. When you really work on it, you feel more comfortable from code perspective. Okay. Anything else? Okay, so everyone, Happy New Year. I hope everything goes well. We can catch up.
Happy New Year.
Yeah, thank you. Sure. All right, see ya. Bye-bye.
Thank you. Bye.